AP Calculus, section 6.4, Separable Differential Equations, page 1. Okay, we talked early in section 6.1 that a differential equation is an equation that contains derivatives. And all of these equations on this page are differential equations. They all contain a derivative here. When we want to find the complete solution to a differential equation, this complete solution, we're looking for hopefully y equals something something with x in it and then plus that c. So a complete solution has the plus c in it. A particular solution is when we actually find out that c value. So these are called separable differential equations because we are going to separate out the variables. And I'm going to multiply by y here and make this y dy. At the same time, let's multiply by dx, which gives us 6 minus 3x squared dx. Then to get y equals, we'll have to anti-differentiate each side. So we have the integral of y dy is the integral of 6 minus 3x squared dx. And anti-differentiating this, we get 1/2 y squared plus some constant c. On the other side, we do an antiderivative, and we have 6x plus, minus x cubed plus a c. All right, these c's are not the same thing, so we do need to differentiate between the two of them. One of them is c1, one of them is c sub 2. Then solving for y, if possible, let's add or subtract this c1 over, and we have 1/2 y squared is 6x minus x cubed plus c2 minus c1. But c sub 2 minus a c sub 1, that's a different constant. So we could say 1/2 y squared is 6x minus x cubed plus a third c. And then multiplying by 2 here to clear the fractions, y squared is 12x minus 2x cubed plus 2c sub 3. But 2c sub 3 is yet a different constant. Also solving for y here, we could take the square root of both sides, which would give us plus or minus the square root of 12x minus 2x cubed plus another constant up here. Let's just call it some constant c. And there we go. That is the complete solution right there. All right, looking at this one over here, number 2, let's multiply by tangent squared y. So we'll have tangent squared y dy, and on the right hand side multiply by dx, to both sides actually, so we'll end up with secant squared x dx. To get the y equals, we'll need to anti-differentiate both sides. And this right side over here, we can do very nicely the antiderivative of a secant squared x dx. That is tangent x plus a c. On this side over here, there is nothing off the top of our head that when you take the derivative gives you tangent squared y. But you remember your pre-calculus, and you know that 1 plus tangent squared theta is equal to secant squared theta. So then we can replace out this tangent squared with secant squared minus 1. So we have secant squared y minus 1 dy. Now we antidifferentiate, and the antiderivative of a secant squared y is tangent y. And the antiderivative of this minus 1 is minus y. Now, plus some constant over here, c. But what we're going to do is say that this constant that's over here actually encompasses the constant from both sides, the left and the right. Just like when over here we got different constants and we subtracted that c1 from both sides and replaced that difference with a third constant. Well, rather than going through those steps, when we have to antidifferentiate both sides, we just write the constant on the right side and accept that that constant over here does in fact encompass the constant from both sides. Now, the general rule of thumb with these differential equations is to solve for y if possible. And in this one right here, it is impossible to solve for y because we have a y on the inside of a trig function and a y outside the trig function. We cannot isolate out that y. Looking at this third one down here, dy dx is e to the x minus y. We are going to have to rewrite this e to the x minus y as, how about e to the x divided by e to the y? Then we can separate out those variables. E to the y dy is e to the x dx. Do an antiderivative on both sides. An antiderivative of an e to the y dy is e to the y plus a c. But remember, we're going to hold that plus c to the other side. And the antiderivative of e to the x dx is e to the x plus ac. All right, now we can in fact solve here for y, and we could just take the natural log of both sides, or rewrite this exponential equation into logarithmic form. And we have y equals the natural log of the absolute value of e to the x plus c. All right, looking at the last one on this page. Let's multiply by y squared. So we'll have a y squared dy. And on the right-hand side, we'll pull this dx up over. So we have x squared times the square root of x cubed minus 3, then dx. Integrate both sides. Oh, you know what? Since I know I'm going to have to do an antiderivative here, I might as well change this x cubed minus 3 from a square root to a 1/2 exponent. Left-hand side we can antidifferentiate very nicely as 1/3 y cubed. Oops. I think I'm going too fast here. Making some mistakes. I'm sorry. 1/3 y cubed plus c, but we are going to hold that plus c to the other side. Over here, oh, we're going to have to do a U-substitution from the last couple of days here. So let's use u equals x cubed minus 3, and du is then 3x squared dx. So when we substitute out, and if you've done enough of these by practice now, you should recognize that this x cubed minus 3 to the half, that's the u to the half. And this x squared dx, that's 1/3 du. And now we antidifferentiate, and we have 1/3 times the antiderivative of a u to the half. Let's see, we'll have u to the 3/2 and a 2/3 out here. There's your plus c. And then Oh, let's replace back this u at the same time that we multiply these two fractions, and we'll have 2/9 of x cubed minus 3 to the 3/2 plus a c. Don't forget, all of this 1/3 y cubed comes down. Again, solving for y, let's multiply through by 3. That'll give us y cubed is 2/3 times x cubed minus 3 to the 3/2 plus a c, and then the last bit, cube root. And there we go. All right. End of page 1. Please join me on page 2.